Hi dears, welcome to Brilliant Katha JEE Mantra Series Part Test 3 Recap video. In this video, we are mainly going to discuss the topics, 3 chapters such as coordination compounds, haloalkanes as well as amines. These 3 topics, one from inorganic chemistry and 2 from organic chemistry. They are important concepts we are going to discuss. Okay, are you ready? Yeah. So, see, in coordination compounds, mainly we have to focus IUPAC nomenclature and isomerism, valence bond theory, crystal field splitting theory, metal carbonyls are there, then stability of coordination compounds, then their application. These are the important things you have to go through. If you have time means you have to check John Teller defects also, you have to go through it, as well as crystal field stabilization energy. That already comes under the crystal field splitting theory. Anyhow, you just go through that one also. Okay, ready? So we can look the first idea. What about the first idea? The salt. Salts are mainly divided into simple salts as well as additional salt. Simple salt means which on dissolution will give simple ions like NaCl, okay, NaCl, KCl, Na2SO4. NaCl will give Na plus and Cl minus. KCl will give K plus and Cl minus, like that. And addition salt means 2 simple salt will combine together to give you what? Double salt. Or else it may be complex salt. Double salt example KCl.MgCl2.6H2O, that's called carnallite. Okay, so once we are dissolving this one in water, it will give you K plus Cl minus, K plus Cl minus, Mg2 plus. Okay, Mg2 plus and Cl minus. Okay, that will give you that one. So that also will give you what? Simple ions. What about complex salt? Complex salt on dissolution will give complex ions. This will give you 4K plus as well as FeCN6 4 minus. So to discuss about this complex salt only, we are having this coordination compound chapter. Okay, yeah, you learn the basic ideas. So here, once we are looking the coordination compounds, it will be appear like this. You can see some counter ion will be there. Either counter ion will be outside the counter ion should be outside the coordination sphere. Okay, coordination sphere, that idea you have to remember. Coordination sphere means that include central metal atom as well as ligand. Sometimes counter ion may be positive, sometimes counter ion may be what? Negative. Okay, that idea you know. So here coordination number means number of ligands or else number of donor atom that attach to central metal atom. Here Cn is donating electron to the central metal atom. Okay, so 6 ligands are there. So that is what is called, coordination number. Okay, some ligands are, in the case of ligands, some ligands are monodentate ligand, some ligands are didentate ligand, some ligands are tridentate ligand, some ligands are polydentate ligand. So the how many atoms in which our ligand is attached to our central metal atom, that is what is called denticity. In that monodentate means only one atom is bound with the central metal atom, like Cl minus, Br minus, ammonia, H2O, CH3NH2, like that. Okay, didentate or bidentate means which can bind to the central metal atom through 2 different atoms. Example, you know, ethane 1,2-diamine, ethylene diamine, NH2, CH2, NH2, as well as oxalate ion, like that. SO4 2 minus, CO3 2 minus, like that. SO4 2 minus and all can act as a what? That can sometime it will be act as a monodentate, sometime it will be act as what? Bidentate. That also possible for SO4 2 minus. Okay, so here once we are going to the third one, so that kind of SO4 2 minus is called flexidentate ligand. Okay, flexidentate. Anyhow, here polydentate ligand means they can bind the central metal atom through more than 2 donor atom. Example is EDTA 4 minus, ethylene diamine tetraacetate 4 minus. Okay, 6. Its coordination number is 6. Okay, next one, ambidentate ligand. Ambidentate ligands means they are monodentate ligand only, but they have 2 donor atom. At a time, they can bind to the central metal atom to only 1 atom. But they have how many donor atoms are there? 2 donor atoms are there, like NO2 minus, ONO, NO2 minus and ONO. Okay, NO2 minus means through nitrogen they are attaching the central metal atom. NO2 minus means they are attaching the central metal atom through N. And ONO means they are attaching the central metal atom through O. SCN minus, NCS minus, NCCN, NC as well as Cn minus. Okay, these all are what? These all are ambidentate ligand. At a time only one atom can bind to the central metal atom. Okay, ready? Next one, chelation. If it is a If it is a more than one dentate means what will happen? They can didentate or polydentate means they can bind to the central metal atom through more than one atom. Automatically they will form what? They will form a cyclic ring-like structure. That is what is called what? Chelation. That phenomenon is called chelation. If chelation is there means you have to keep it in mind. Chelation is there means the stability of the complex ion complex will be more. Okay? Yeah. We can go to the next idea. That is actually isomerism. It's a very important idea. Very important idea. Many examination. Okay. Many times the same thing from this area, they were usually asking question from this area. Okay, don't forget, keep it in mind. So here in isomerism, mainly we have to learn about structural isomerism, stereoisomerism. The basic idea, you know what is isomerism. They have same molecular formula but different chemical properties. If it is structural isomerism means they have same molecular formula but different structures. Different structures in the sense different types of bonds. And stereoisomerism means they have same molecular formula but different stereo aspects, spatial arrangements, or same bonds but different arrangements. That's the idea. Okay, ready? In that itself, we have to look about what? That structural isomerism again divided into ionization isomerism, hydration isomerism, linkage isomerism, and coordination isomerism. In that, ionization isomerism means that arises when the counter ion in the complex salt itself a potential ligand and can displace a ligand which can become the counter ion. Simply the thing is that simply we can tell that what? The counter ions are interchanging. Counter ions and ligands can interchanging. For example, here in the case of ionization isomerism means they are actually isomers. They are having same molecular formula but they will give different ions in solution because of the interchanging of ligand and counter ion. See, in the first case you can see here SO4 is the counter ion. Okay, SO4 is the counter ion. So that time they are giving, these are the ions they are giving. In the second case you can see Br is the counter ion. That time SO4 goes as what? Ligand. So once they are ionizing, this is the ions you are going to get. Okay, so in this Br and SO4 are interchanging. Okay, that's the thing happening. So you are getting different ions but same molecular formula. That is what is called ionization isomerism. You know the idea. I am simply one more time I am simply refreshing. That's all. Okay. Yeah. Next one, hydration isomerism. The name itself, hydration. That means water molecule. Hydration, water molecule. So here the isomerism, in this isomerism, the isomers have same molecular formula but the number of water molecule present as ligand as well as hydrate in the sense hydrogen bonded water molecule, that number will be different. Okay, here you can see isomers differ by whether or not a water molecule is directly bonded to the metal ion or merely present as a free solvent molecule. That may be hydrogen bonded or in lattice, maybe it may be present like that. Okay, free solvent molecules. So here you can see Cr H2O 6Cl3. Here H2O is 6H2O present as what? Present as ligand. In this case, 5 H2O only present as ligand, 1 H2O as hydrate outside the coordination sphere. Idea clear? So whenever it comes means that is what is also called solvation isomerism. In that case, their color and all will change. Okay, idea okay, clear? Yes, we can go to the next one. We can go to the next idea. What's the next idea? That is linkage isomerism. Linkage isomerism is shown by, you have to keep it in mind. You have to identify that one. If there are any ambidentate ligand is there means they will show linkage isomerism. Okay, yeah, here arises they are having same molecular formula but different linkage atom. In the first case CONH3 here nitrogen is attached to the central metal atom cobalt, but here CONH3 times ONO, here oxygen is attached to the central metal atom. Remaining all are same. Ready? And the next one, coordination isomerism. They are actually, you must have to remember, in coordination isomerism, both anion as well as cation are coordination spheres. In that, the ligand attached to the central metal atoms are interchanging. They have same molecular formula. We can take one example. You can see CONH3 6, CrCN 6. Here the first coordination sphere is positive, second coordination sphere is negative. In the first coordination sphere, ammonia is connecting with the cobalt. In the second molecule, you can see second molecule, ammonia is connecting with the chromium. So that the central metal atoms are interchanging. In this case, you have to remember, whenever you are interchanging the central metal atom, their coordination number should be same. Then only it is possible. So cobalt along with the 6 ammonia are there. Here chromium along with the 6 cyanide are there. But in the isomer, it is just opposite. Ammonia is now present with the chromium and cyanide is present with the cobalt. Idea clear? You can easily identify. Okay, yeah. Next, once we are going to the next idea, that is what is called stereoisomerism. In stereoisomerism, mainly, guys, you have to remember the number of stereoisomers. The stereoisomerism is mainly two types: geometrical isomerism as well as optical isomerism. In geometrical isomerism, that arises mainly due to different possible geometric arrangement of the ligands. This is only possible in heteroleptic complex. Heteroleptic complex means central metal atom bind with different types of ligands. You see here, coordination number 2 and 3, no geometrical isomerism. Coordination number 4, tetrahedral, no geometrical isomerism. Okay, and square planar, various cases are there. In square planar, Ma4 means no geometrical isomerism. Here there is no heteroleptic complex. All are same. And Ma3b means no geometrical isomerism. Ma2b2 means two geometrical isomerism. One cis, one trans. Cis and trans, you know, same kind of atoms comes in the same side. Then there is cis. Same kind of atoms comes opposite side, trans. Okay, that idea you know. And MABCD means, see, A, B, C, D. All the ligands are different. That time 3 geometrical isomerism is possible. 2 cis and 1 trans. 2 cis and 1 trans. Then MAB twice. MAB twice. AB is what? AB is a heteroleptic didentate ligand. Here AB. Okay, didentate ligand. So how many geometrical isomerism is possible? 2 geometrical isomerism is possible. One is cis, another one is trans. And similarly, geometrical isomerism in the case of coordination number 6. Coordination number 6. Ma6, no geometrical isomerism. Ma6, no geometrical isomerism. Ma5b, no geometrical isomerism. Okay, and Ma4b2, 2 geometrical isomerism, either cis or trans. Cis or trans is possible. And if it is Ma4bc, A, B, C are monodentate ligand. That idea you know. Ma4bc means 2 geometrical isomerism, one cis and one trans. And Ma3b3, there is no cis and trans. Only one special case you learned, that is Mer and Fac. All the atoms, okay, all the similar ligands are comes in the phase. See, comes in the phase means 2 are in the same plane, one above or below. That is what is called fascial. And they are come in the meridian, in the same plane. Three ligands are comes in the same plane. A. They are come in the same plane. They are actually called meridian. So that is possible only in the case of Ma3b3. And again Ma2b2c2. Here 5 geometrical isomerism is possible, as well as MABCDEF. All ligands are different means 15 geometrical isomerism possible. How many geometrical isomerism possible? 15 geometrical isomerism possible. That numbers you have to keep it in mind. Ready guys? Yeah. We can move to the next idea. Then optical isomerism. Optical isomerism means they have different optical activity, but same chemical formula. Okay, that is optical isomerism. So here you can see dextro as well as levo is there. Dextro means what? They have a tendency to rotate the plane polarized light towards right. Levo means what? They have a tendency to rotate the plane polarized light towards left. Both are non-superimposable mirror images. So that's why they are called what? Enantiomers. So here in the first case, they given MABCD. There is a asymmetric center should be there. MABCD type means no symmetry. 2 optical isomers are possible. One dextro, one should be levo. Which one is dextro, which one is levo, that we can find out by using polarimeter tube. Okay, and if it is Ma3b, Ma3b means if there any symmetry, if there any plane of symmetry means there is no optical activity. That idea you have to keep it in mind. So here you can see next one, this one, the next one I given is MAA thrice. MAA thrice have 2 optical isomerism. So you have to remember in the given case, either along with the central metal atom, all the ligands are different. Then optical activity is possible. Or else at least one you can check MAA3 and all this means that's actually didentate ligands are present, means then also symmetry is not there. So that time also they can show what? Optical activity, like that you can remember. Here once you are coming to here, see here it is Ma3b3. Ma3b3 means they have plane of symmetry, therefore optical activity is not there. That idea you have to keep it in mind. So just to remember, if there any didentate ligands are there means there possibility of what? Optical activity. Okay, yeah. Next question, next idea here, coordination compound. I mean, next question they usually used to ask from these coordination compounds, different types of bonding. Which are the different types of theories we are learning related to coordination compounds, how the coordination compounds are forming. Mainly valence bond theory, then Werner's theory, then crystal field theory. The same valence bond theory, basic ideas you are learning in chemical bonding and molecular structure. Okay, then Werner's theory is there, then crystal field theory is there. In that first theory, once we are looking, the Werner's theory, that's a very important theory. In this, actually, here they are talking about the valencies. There are mainly two types of valencies present in a coordination compound. First one is primary valency, second one is secondary valency. These primary valencies are ionizable and non-directional. Okay, non-directional, there is no direction and satisfied by anions, and it represent, this primary valency represent what? Oxidation state of the metal. And the secondary valency means non-ionizable, that we cannot break, non-breakable. They have some direction. And satisfied by what? Ligands. Satisfied by ligands, and that represent what? Cn means coordination number of the metal. Here you can see CrH2O6Cl3. Here the oxidation state of chromium is +3. So that represent what? Primary valency, because 3 Cl are there that are breakable. And 6H2O are there, that's the coordination number, that's the secondary valency. So breakable one is primary valency, unbreakable one is what? Secondary valency. That idea you have to keep it in mind. Okay, yeah. Anyhow, next one, valence bond theory. In this valence bond theory, metal ligand bond arises when a filled ligand orbital overlap a vacant hybrid orbital of metal. I mean, the ligands are coming with the electron pairs. That electron pairs containing orbital, they are overlapping with what? Central metal atoms vacant orbital. Then there is a bond is forming. Metal ligand overlapping is happening. That is what is called valence bond theory. There are different types of overlapping. Before that, they will undergo intermixing. Before the overlapping, the central metal atom will undergo intermixing. Like what? If 4 orbitals are there, 4 ligands are coming, means they will intermix one s orbital, 3 p orbital, they will give you tetrahedral. And 4 another possibility is there, 1d and 1s and 2p square planar, and 5 means sp3d trigonal bipyramidal, and 6 means sp3d2 or d2sp3. sp3d2 means octahedral, d2sp3 means that also octahedral. And here this d2sp3 as well as, see, this d2sp3 as well as dsp2. There, the inner d orbital they are taking. That's why they are called inner orbital complex. Inner orbital complex. And this you can see sp3d2, sp3d. They are taking outer d orbital. They are called outer orbital complex. Outer orbital complex. And here one more thing we have to remember. The strong field ligands are ammonia, Cn-, carbon monoxide, which forces strong field ligand means which forces pairing. And other means you have to remember that one. Then one more thing, outer orbital complex, that means sp3d2, sp3d, they are actually high spin complexes. There is no pairing, so high spin complexes. Inner orbital complexes are generally, that means d2sp3, dsp2, they are actually what? Low spin complexes. Okay, their spin is less. They will be mainly they are paired automatically low spin complexes. Okay, and again once we are going to the valence bond theory, 2 examples I given here. Okay, you already went through many examples. 2 examples I given here to understand. Here CONH3 6 3+. This is the complex ion. Here central metal atom is cobalt. Its electronic configuration is 4s2 3d7, and in our complex cobalt is 3+. That means that 4s containing 1 is missing, as well as 3d 1 is missing. So 3d6. 3d6 means I can draw like this, but ammonia is a strong field ligand, pairing will take place. How many ammonia molecules are coming? 6 ammonia molecules are coming. Automatically 6 orbital is required. 1, 2, 3, 4, 5, 6. So 2d orbital, okay, and 1 s orbital and 3p orbital they are mixing. They will form what? d2sp3 hybrid orbital. D2sp3 hybrid orbital. They are taking inner orbital. Okay, inner orbital they are taking. That's why they are low spin complex. There is no spin. All spin are cancelled. Okay, all are paired. That's why diamagnetic. They cannot show any color, and their shape is octahedral. But once we are looking about CrNH3 6 3+, you can see here chromium is 4s1 3d5. Chromium is 4s1 3d5. That's the general electronic configuration. But in our complex, chromium is chromium plus 3. That time 3 electrons are missing, 3d3 will come. You can see here 3d3 are there, but there is no pairing. There is no pairing. There is no possibility. So there is no pairing in the case of Cr3 6 3 plus. So they will take the same they will take. You can see that is D2sp3. But here more number of unpaired, more than one unpairs are present. That's why high spin complex. Minimum one unpaired is there, means there is paramagnetic. This is 3 unpairs are there, more paramagnetic. And it is colored because unpaired electrons are there, means it is colored and octahedral. This much idea, so many exceptions also we learned in the classes. Okay, so if you don't know, means you can comment it. We will make the video along about that. Okay, don't worry. Okay, so we can go to the next one. That is crystal field theory. The last theory about the coordination compounds we have to learn. Okay, so here in crystal field theory, the idea is metal ligand bond is purely electrostatic. Okay, purely ionic. Okay, that arises from electrostatic interaction between what? The metal and the ligand. And anionic ligands act as a point negative charge, and neutral ligand act as what? Dipoles. So an isolated gaseous metal atom, the d orbitals are degenerate, and the degenerate means they are having same energy, and the degeneracy is maintained in spherically symmetrical field. That degeneracy is around the sphere, or everywhere it is same. Everywhere the energy is same. Okay, the degeneracy of the d orbital split in the ligand field. Whenever ligand approaches the central metal atom, that degeneracy will break. And pattern of splitting depends upon the nature of crystal field. In which direction your ligand is coming, accordingly the splitting will take place. So there are 2 types of crystal field splitting. You learned first one is what? Octahedral crystal field splitting. Second one is called what? Tetrahedral crystal field splitting. If your ligand approaches along the axis, then that is called the octahedral crystal field splitting. If your ligand approaches towards in between the axis, or else along the plane, that is called a tetrahedral splitting. In the case of octahedral splitting, these 5 orbitals, that is degenerate d orbital, that will undergo an energy increment. Okay, they are excited state. Then they will split it into 2 energy level, dx square minus y square, dz square. Dx square minus y square as well as dz square, they are collectively called Eg. Eg means doubly regenerated orbital, degenerated orbital. And here this will split into T2g. T2g means dxy, dyz, dxz. So they are actually T2g, triply regenerated orbital, degenerated orbital. Okay, they will split into 2 different energy level, and this center is called Barry center. From Barry center to Eg, always 3/5 of delta O, and Barry center to this T2g, always 2/5 of delta O. And the energy difference between T2g and Eg, that is what is called delta O. Okay, that idea you know. If it is tetrahedral, means the ligands will approaches along the plane. So the orbitals which lies along the plane, their energy will increase. Which all are the orbital? They are laying along the plane. They are dxy, dyz, dxz. So their energy level will increase. They are called T2. And the one which lies along the axis, that is dz square, dx square minus y square, their energy level will decrease. That is E. So the energy difference between E and T2, that is what is called what? Delta T. Then from Barry center to T2, always 2/5 of delta T. From Barry center to E, that is 3/5 of delta T. Okay, and this delta T as well as delta O, once you are comparing, delta O is always greater than delta T. That idea also you have to remember. You already remembered, I hope so. And the factors affecting crystal field stabilization energy. Which all are the things affecting the crystal field stabilization energy? First one, oxidation state of the metal. Your oxidation state of metal is increasing, means automatically the crystal field splitting energy is increasing. And nature of metal. If your metal belongs to 5D series, then more splitting. 4D series, less splitting. 3D series, very less splitting. The splitting between T2G and EG, or else T2 and E, the splitting increases upon which transition series your central metal atom belongs to. Okay, and number of ligands. More means more will be the crystal field stabilization energy. That delta O, delta T will be more. Okay, and nature of ligands. Nature of ligands means these are the ligands. Strength, field strength increasing order. That's what's called spectrochemical series. That idea you learned. So the one which all are greater than water, they are called strong field ligand. Those are lying below that one, they are called weak field ligand. Here you can see iodine, Br minus, Cl minus, F minus, all are halides. Their field strength is less than that of water. That is one of the demerit of this one. Anyhow, according to this theory, they are coming just below. And ammonia, cyanide, carbon monoxide, they belong above the water. So they are strong field ligand. In their cases, pairing will take place. Those who below, no pairing. Okay, let's look about one example. Once we are looking, filling of electrons in splitted d orbital. Suppose I am having D. In D, okay, in D, 4 electrons are there. How many electrons are there? 4 electrons are there. 1, 2, 3, 4 electrons are there. Okay, D4 is there. Then how I will fill in the splitted orbital? One will be go here, another one will be go here, another one will be go here. And the 4th electron, where it will go? For that they given the condition delta O less than P. That means pairing energy is the energy required for pairing. If pairing energy is more, means there is no pairing, because the next electron go to pair in the same orbital, means there is a repulsion. To avoid that repulsion, they required some energy that is called pairing energy. If pairing energy is more, means no pairing. Keep it in mind. If pairing energy is more, means no pairing. So the 4th electron will go to here. So delta O less than P means, if it is D4 configuration, means T2G contain 3 and EG contain 1. That is the possibility. And if delta O greater than P, I mean if your ligand is strong field ligand, then splitting will be more. The T2G EG distance will be more. If it contain 4 electron, means where it will go? D4 means where it will go? 1, 2, 3. This energy gap, this delta O is more. So the 4th electron cannot go to there, but their pairing energy is less, so that will go and pair. So in that case, delta O greater than P means D4 comes, means we are filling the electrons like T2G4, EG0. Okay guys, can you understand? Yeah. Next, again we have to look about what? Metal carbonyls. It's a favorite topic for the questionnaires whenever they are asking the question for the JEE examination. Metal carbonyl. Last session also metal carbonyl related questions was there. So here, that carbon monoxide is bonded with what? Central metal atom. That is what is called a central metal atom, like nickel, iron, manganese, etc. In this case, the central metal atom oxidation state is 0. Okay, so this is NiCO4, this is FeCO5, Mn2CO10, like that. Okay, last question was like this. In cobalt forming, this is cobalt. Okay, cobalt around it. Cobalt, how many cobalt are there? Cobalt 2. How many carbon monoxide are there? See, how many? 1, 2, 3, 4, 5, 6, 7, 8. Okay, in this case, in between cobalt, how many cobalt carbon monoxide cobalt bridges are there? How many are there? 1 as well as 2. 2 are there. So that was the question before. So you have to remember like that. Okay, that metal carbonyl bonding is very important. In that case, how the bonding is possible? So metal carbonyl bond, this is carbon monoxide, this is metal, along metal, 5d orbitals are there. In carbon monoxide containing sigma electron. See, sigma electron. Carbon monoxide contains 14 electron. The last electron is in sigma. Okay, sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2, pi 2px2, pi equal to pi 2py2, then sigma 2pz2. That sigma 2pz2 electron they will donate to what? Central metal atoms vacant d orbital. That bond is sigma bond. So central metal atoms charge is 0. Whenever they are gaining electron from the ligand, means its charge become negative. It become unstable. So what it will do? It will donate that electron back to the carbon monoxide. One way they will receive, another way they will donate. So they will donate to where? Pi star orbital of the carbon monoxide. That's what's called a pi bond. So one way they will receive, receiving is sigma bond, donating is pi bond. Okay, 2 pi bonds and 1 sigma bond is possible. So in between metal and carbon monoxide, 2 types of bonds are possible, sigma as well as pi. So that's why that bond is called what? Synergic bonding. Okay, that idea you learned, guys. And finally, the last thing you have to remember from here is importance of coordination compound, significance in biological system. We know the idea. Chlorophyll is actually a complex of what? Magnesium. Hemoglobin is a complex of iron. Vitamin B12 is a complex of cobalt. Okay, cyanocobalamin we know, and significance in medicinal chemistry. See, cisplatin is an anti-cancer agent, and if it is transplatin means what will happen? That will induce the cancer. Okay, that cis and trans have that much importance. And EDTA is actually lead poisoning. For that, to remove that one, we are usually using what? This EDTA. EDTA will entrap that lead, and it will come out through the excretion. That idea we are using there. And extraction process of metals like silver and gold, we are using what? The concepts of what? This idea, this concepts of coordination compound idea we are using, as well as Wilkinson catalyst. Wilkinson catalyst, where we are using hydrogenation of alkene. All are what? That is, all are what kind of things? Coordination compounds only. These are the important ideas related to what? Coordination compound. You have to go through it. What is Wilkinson catalyst? What's the structure of Wilkinson catalyst? If you have time, means you have to go through it, guys. Okay, that's all the idea about the chapter coordination compound. So dears, next chapter is haloalkanes and haloarenes. In this chapter, mainly you have to focus the preparation of haloalkanes and their properties. Properties in the sense their reactions. Nucleophilic substitution reaction, reaction with the metals, as well as what? Reaction with the metal, and elimination reaction. These are the important things you have to remember from here. Okay, ready? Yeah, here once we are going to look this one, first of all, we have to focus on preparation of alkyl halides. In that case, we are preparing from alcohols. An alcohol is there that you are treating with HX and ZnCl2. There is nothing. That's actually what? HCl and ZnCl2 if you are taking in, that is what is called a Lucas reagent. If it's a tertiary alcohol means that will give fastly the turbidity. Okay, if it is a secondary alcohol means after some time it will give. If it's a primary means you have to heat it to get the turbidity. That idea you learned. The same idea here from that the turbidity is actually because of what? Haloalkane, Rx. Okay, so tertiary will give more than secondary than primary. This alcohol I am talking, okay, will give this haloalkane. And the second thing, haloalkane we can prepare from what? ROH alcohol by treating with the PX3. You will get RX. Similarly, not only PX3, not only PX3, you can take PCl5 also. PCl5 once you are treating, you will get RCl. So this is the reaction. ROH once you are treating with the PCl5. This here it will break, here it will break. HCl, RCl and POCl3 you will get. And again, ROH you are treating with SOCl2, thionyl chloride, you will get RCl, and this reaction is called Darson's procedure. Here, this is the best method to prepare haloalkane, especially chloroalkane. Okay, chloroalkane, because here the products, other products are byproducts are gaseous state. So we don't want to separate them. Easily it will go out. We will get RCl alone. Okay, yeah. Next one, another preparation method is from alkanes. Alkanes you can treat with what? Halogen in presence of sunlight. They will give you a mixture of haloalkane. Okay, that may be mono or di or tri or tetra. Yeah. Next one from alkenes. Towards alkenes you can treat with hydrogen halides. Hydrogen halides. If you are treating with hydrogen halides, that is actually going through the carbocation mechanism, Markovnikov addition. That means rich become richer. Hydrogen will go and attach with more number of hydrogen containing carbon. And here, if you are treating with the peroxide, you can see that this hydrogen is going with a more number of, that hydrogen is going with a less number of hydrogen containing carbon, or CH2, CH2Br. Br will go and attach here. Just opposite, anti-Markovnikov addition in presence of peroxide. Or else, you can add, in alkene, you can add X2 in bar CCl4. I mean Cl2 bar CCl4 if you are treating means at a time, both cases, both double bond will break and chlorine will be added there. That idea you know. Okay, yeah. We can go to the next one. We can go to the next one by allylic and benzylic halogenation. For that, we are using a compound that is what is called bromine HNu bar NBS, N-bromosuccinamide. Allylic bromination, we are using this one, N-bromosuccinamide. Allylic means what? CH3, CH, double bond CH2. sp2 hybridized carbon, that attached sp3, that carbon is called allylic carbon. Or else benzylic carbon. Benzylic means benzene ring that attached CH3, that attached carbon. That is called benzylic carbon. So sp2 attached sp3 is called what? sp2 attached sp3 is called what? In benzene ring means benzylic. In normal chain means what? That is called allylic. Okay, there we can do. I mean, if you are treating this one with bromine in presence of NBS, N-bromosuccinamide, where this bromine will be go and attach. Here it will be go and attach. That means in allylic position only it will go and attach. You can see allylic position, that bromine will be go and attach. That's it. Yeah, clear, ready. We can go to the next idea. This is the next idea, preparation of alkyl halide by halogen exchange. The previous methods are mainly for chloroalkane, chlorine containing alkanes. Okay, haloalkane in the sense in that chloroalkane is there, fluoroalkane is there, bromoalkane is there, iodoalkane is there. In that we can use that method only for chlorine. Here if you want to prepare iodoalkane means you can do the halogen exchange by using Finkelstein reaction. Finkelstein reaction will give halo means iodoalkane they will give. For that haloalkane you have to take, chloroalkane you have to take, that you have to treat with the sodium iodide in presence of acetone. So that halogen will be exchanged with the iodine. Okay. Then again Schwarz reaction, that is only for the preparation of fluorine. RF you will get. Similarly, Hunts-Decker reaction is there for the preparation of what? Preparation of bromine. That also you learned. That name also you learned. Okay, you have to go through it. Next again, nucleophilic substitution. There are mainly two types, SN1 as well as SN2. In SN1 you can see RX is there. Nucleophile is there in presence of solvent. That X will be substituted by your nucleophile. SN1 means that will be taking place in two steps. SN1 means substitution nucleophilic unimolecular, that takes place in two steps, that will go through that is undergoing through the carbocation mechanism. So if more the stable carbocation means more will be the reaction rate. That idea you have to keep it in mind. Here you can see I gave one example. Here CH3 that is connecting with a carbon and chlorine. Here in first step, slow step, this chlorine will take the electron and it will be become carbocation. You can see that will be become what? This will be going and see here you can see CH3 and plus, they were forming carbocation. Then again water you are adding, whenever water you are adding means that they can provide what? OH minus. From here they can provide OH minus. Okay, you can use an alkaline medium, OH minus. That OH minus will go and attach there. Here in racemization is possible. That means this OH minus can either come and attach towards the front or else from back. So SN1 means what? You have to remember that idea. SN1 means two steps. Okay, two steps reaction and carbocation mechanism and racemization. This much idea you have to keep it in mind. Okay, two steps, carbocation and racemization. And if it is carbocation mechanism means what? Tertiary is more fasterly giving that reaction than secondary than primary. And among RI, RBr, RCl, RF, this RI will give more fastly this reaction than RBr because CI bond we can break it easily. That's why. And as well as this, which solvent is suitable for this one means polar protic solvent like H2O, ROH, RCOH. They are polar as well as protic, proton donors. Okay, and weak nucleophile is preferred. Weak nucleophile like H2O, NH3, RNH2, like that weak nucleophile is preferred for this reaction. So we got the idea related to what? Which haloalkane we have to take, which nucleophile we have to take, which solvent we have to take. So dears, next one is SN2 reaction. SN2 reaction means substitution nucleophilic bimolecular reaction. This reaction taking place in single step. Whenever, see, you are taking an haloalkane, you are treating with the nucleophile. The nucleophile is coming and attaching to the carbon. At the same time, this halogen is leaving. So this is an intermediate state, but we cannot tell it is intermediate transition state. It is highly unstable because around carbon 5 bonds are coming. So whenever this nucleophile is coming, but it can come only through the backside. Backside attack only it can do because whenever halogen is there, that time it is coming through the back. So it will give you what? Inversion product. If it is dextro means that will be levo. That's the concept. Okay. Yeah. So this will be possible. This will be purely depends on what? Steric hindrance. So primary will be giving more SN2 product than secondary than tertiary. And RI will give more than RBl, than RCl, than RF. And here the solvent, possible solvent is polar aprotic solvent. That means acetone, DMSO, okay, as well as DMF, dimethyl formamide, like that only, that will give what? This SN2 reaction. And here, the list of nucleophiles I given, in NCERT it is there, you can go through that one. Okay, to get OH minus, you have to take NaOH or KOH. To get nucleophile H2O, you can take what? H2O, that time also we will get alcohol. And to get RO minus, we can take NOR, like that, I minus, NH2. If you are taking CN minus if you want means, see, that all are the important thing. CN minus if you want means, you have to take KCN. AgCN if you are taking means, you will get what? NC. You will get NC, isocyanide you will get. That idea you have to go through it. And if you want to get hydrogen means, you have to take what? Lithium aluminum hydrate. for the substitution. So that nucleophilic substitution list I given, you have to go through it, guys. Okay, yeah. Next one, again, the last reaction, the second reaction, okay, the second reaction is of alkyl halides, that is actually dehydrohalogenation, or else it is called beta elimination. They given one haloalkane that you are treating with alcoholic AOH. Aqueous KOH means substitution. Alcoholic KOH means what? Alcoholic KOH means elimination reaction. This is also called elimination, beta elimination reaction. Beta elimination reaction. Okay. So in this case, you can see the halogen attached carbon is called alpha carbon. That attached carbon is called beta carbon. So whenever you are treating with alcoholic KOH, from alpha, one halogen, from beta, one hydrogen will go. In between alpha and beta, double bond will come. Two possibilities are there. Two possibilities are there. Which one is the major product? That is explained by using Say's-F rule. Say's-F rule. The major product will be always more substituted alkene. So this is the more substituted alkene. So that means double bond comes inside. Will be the major product. Like that you can remember. Okay. So this is the more substituted alkene. You can see that is like this. CH3, CH, okay, double bond, CH, single bond, CH3. So around this carbon-carbon double bond, two substitutes are there. Two are there. Okay, once we are coming to here, the second product CH3, CH2, CH double bond CH2. In this case, here only one substituents are there. More substituted product is more stable, more major product. That's what is called beta elimination. That idea also you have to keep it in mind. Then again, the property is the last property, reaction with the metals. If our haloalkane that react with the magnesium, in presence of dry ether, you are getting Grignard reagent. It is highly reactive one. This Grignard reagent, if I am keeping outside, you just remember RMGX, if I am keeping outside, that will react with the moisture. That will give you what? RH plus MgOHX. You will get a alkane. Also, one more thing you have to remember, always in between this RMG, that bond will break. That bond is what kind of bond? Covalent bond. MgX bond is what bond? Ionic bond. Okay, that idea you have to keep it in mind. Again, reaction with the sodium. If two haloalkanes are there that you are treating with the sodium and dry ether, you will get a alkane with a double number of carbon atom that you learned Wood's reaction. If you are taking 2 haloarenes, then you will get sodium and ether. If dry ether, if you are treating means you will get biphenyl, that is Wittig reaction. And if you are taking one haloarene as well as one haloalkane, you will get what? A methyl substituted benzene. That is what is called a Woods-Wittig reaction. 3 reactions you learned. Okay, so that's all about the idea about what? The chapter haloalkanes and haloarenes. From there, one more idea you have to go through it. Okay, if you have time means you have to go through what? That nucleophilic substitution is not possible in the case of haloarenes, and the electrophilic substitution reactions of chlorobenzene. That idea also you have to go through it. And if you have time means you have to go through the Dow's process, how to prepare that phenol, or else tri-substituted phenol. I mean the picric acid and all. Okay, from where the chlorobenzene, that much idea, that all conversion also you have to go through it. Possible, if you have time means you have to go through it. Try to do maximum problems. Okay, try to do maximum problem, because all the organic chemistry topics are interrelated. We cannot tell that this is only from haloalkane, this is only from amines. We cannot tell like that. You have to go through it. All are interconnected. So once you are going through the entire topics means you can easily handle it. The questions will be designed like that only. Okay, yeah. So dears, next chapter is amines. This also related to haloalkanes and haloarenes. Many concepts are related, interrelated here. Okay, so here first of all we have to learn about what? Preparation of amine. That's actually from alkyl halides. Okay, that is what is called ammonolysis. So here you are having alkyl halides. That alkyl halides you are treating with what? Ammonia. If you are taking excess ammonia means you will get only primary amine. Okay, primary amine you will get. That again treating with the RX, that will be giving you secondary amine. That again treating with the RX, that will give you tertiary amine. That again with RX, quaternary ammonium salt. So if you are taking alkyl halide excess means you will get a mixture of primary, secondary, tertiary and quaternary ammonium salt. And if you are taking Ammonia excess means only primary amine you will get. Okay, that idea you know, guys. Then next one is Gabriel thalamide synthesis. It's a very important reaction. We already learned the Gabriel thalamide synthesis. Okay, so this is phthalic acid that I am converting it into thalamide. Okay, that thalamide is treating with an base and alcoholic KOH we are treating. That will be converted to that. NH will be converted to NK. Okay, potassium thalamide. Then you are treating with a haloalkane. That haloalkane you are taking, that is only haloalkane. That's only haloalkane is possible. Okay, haloarene we cannot. Okay, this only for the preparation of primary aliphatic amine only we can prepare by this method. Okay, that idea you have to keep it in mind. Primary aliphatic amine only we can prepare. If you want to prepare RNH2 means, you have to take RX. You have to take RX. Okay, so that RX I am taking, that R is going, then you are treating with NaOH, you are getting RNH2. Here it is breaking. Okay, here it is breaking RNH2, you are getting that reaction, you know. So here that chlorobenzene we cannot prepare by using this method, because if you want to prepare chlorobenzene means aniline you cannot prepare, because if you want to prepare aniline means you have to take chlorobenzene. Chlorobenzene once you are breaking, that is you are getting is phenyl carbocation, that is highly unstable. So that reaction is not possible for that. That idea you have to keep it in mind, guys. So again, the another idea is from reduction reaction from nitro compounds, nitrile compounds and amide compounds. And nitro compounds we can reduce by using hydrogen in presence of palladium. Okay, or else in sodium in presence of ethanol. We can use, or else tin bar HCl, iron bar HCl, like that we can use it. Okay, the best cheapest method is iron bar HCl. Okay, next again reduction of nitriles. Cyanide compounds are there that you can reduce to amines. Hydrogen is adding, that is what is called reduction by using lithium aluminum hydrate. Okay, lithium aluminum hydrate or hydrogen or sodium in presence of ethanol, you can use reduction of amide. So that reducing agent you are using is lithium aluminum hydrate or hydrogen and nickel. From where? Amide also, RCONH2, that you can convert it to RCH2NH2. And one more thing, one more very important reaction you learned is Hofmann bromamide degradation reaction. There you are having one amide, RC double bond ONH2 is there, that you are treating with what? Bromine in presence of KOH. That time this CO is going and directly that NH2 is attaching RNH2 you are getting. Primary amine you are getting. That idea you have to keep it in mind. Here why it is called degradation? Here the number of carbon is N+1. That one carbon is decreasing here. That's why it is called a degradation reaction. Okay. There is some rearrangement also there. That reaction mechanism also you learned. Okay. Yeah. See. Next one, the properties of amines. Once we are going to the properties of amines, first one is acylation. You can do the acylation in amines, that instead of that H, you can introduce the group what? CH3CO group by using acid chloride. By using acid chloride, you can introduce, okay, there is acyl group. CH3CO group is called acyl group that you can introduce, or else by using acid anhydride, CH3CO twice, you can introduce that one. That also very important reaction. Then again, next is carbyl amine reaction. Carbyl amine reaction or else isocyanide test. A primary amine, either it may be aliphatic or aromatic. If you are treating that one with chloroform and KOH, it will give you a isocyanide having foul smell. If I am taking, see, if I am taking aniline, and if I am treating this one with what? Chloroform, CHCl3 and KOH, that will give you what? Phenyl isocyanide. That's having foul smell. That idea you have to remember. That test is called what? Carbyl amine reaction or carbyl amine test, isocyanide test. Next one, reaction with nitrous acid. If you are taking a primary aliphatic amine and if you are treating with HNO2 you will get from NaNO2 and HCl. That will give you what? Alcohol, you will get alcohol. If you are taking a primary aromatic amine, that means aniline you are taking and you are treating with NaNO2 plus HCl at 0 to 5 degrees Celsius. Okay, that means ice cold temperature, it will give you benzene diazonium salt. This benzene diazonium salt, a lot of reactions are there, like coupling reaction, displacement of nitrogen reaction, that also you have to go through it. Okay, that's very, very important. Okay, yeah. Next again, the distinction between primary, secondary and tertiary amine, that also given by using Hinsberg reagent. One Hinsberg reagent is benzene sulfonyl chloride. Okay, benzene sulfonyl chloride that you are treating with the primary amine, that will give you a compound. That compound is soluble in alkali because of the presence of acidic hydrogen. That idea you learnt. Yes or no? Yeah. And if it is secondary amine means you will get a compound once it is treating with a Hinsberg reagent, you will get a compound. That compound is insoluble in alkali. But if it is a tertiary amines mean it have no reaction with the Hinsberg reagent. That idea also you have to keep it in mind. Okay, that is actually where we are using to distinguish primary, secondary and tertiary amine. And again, once we are coming to the basic strength of amines. In gaseous state, basic strength only depends on what? The inductive effect. In gaseous state, only inductive effect. Gaseous state means more inductive effect means more basic. You know, this nitrogen that contain lone pair is there. That lone pair they are donating, so they are Lewis bases. So more ability to donate that one means they are more best bases. So here, because of this alkyl groups are electron donating group. The electron density of nitrogen increases, so automatically they can easily donate. Electron density increases means they should be act as a better donor. So that's the best base in gaseous state. Tertiary is more basic than secondary, than primary, than ammonia in which case gaseous state. But once it comes to the liquid state, that you learned in the case of liquid state, in the case of methyl substituted. See, in the case of methyl substituted, CH3 twice NH. Secondary is more basic than CH3NH2. Primary than CH3NH2 than tertiary. CH3 thrice Na. And in the case of ethyl substitute, this is secondary, primary and tertiary. In the case of ethyl substituted, C2H5, okay, C2H5 twice NH, secondary is more basic than tertiary, C2H5 thrice N than C2H5 NH2. Okay, that idea you have to remember. Secondary, tertiary, primary. Then ammonia and aromatic amines are less basic. Why? I mean aromatic amine means aniline is less basic because that lone pair is taken for what? That resonance. That's why it is not available for donation. That idea also you have to keep it in mind. So here in aqueous state we are telling that basic character because of inductive effect as well as hydration effect. That two idea we are using. So this much idea if you are going through means along with that you have to go through what? That diazonium salts and their reactions. Okay, diazonium salts and their reaction. That means coupling reaction. I mean the dye giving reaction as well as what? That displacement of nitrogen reaction. That all are the things if you learn means this chapter also over. So go through every reaction, each and every reaction, and try to solve maximum questions, dears. That will be the best method. Okay, our time is very less, so you have to go through the maximum questions. Once you are going through the questions, practice the questions and try to remember the theories. That's the better thing. Or else if you are spending a lot of time in theory means it will be a worst thing because you won't get the time to solve the problems. So that will be going to be a hectic situation. So no need. Instead of that, you go through the questions. That time if you are not getting means go back to the theory and learn. So study well. You can. We will be there. The brilliant Qatar is there along with you up to once you reach to IIT, okay, or NIT, we will be there, guys. Okay, so happy learning. Thank you so much.